Hello everyone, this is Cadet Chauvin, and today I'm going to make a video on conservation of angular momentum. I'm going to use a pen and a piece of paper to demonstrate the conservation of angular momentum. So first, I'll take a piece of paper and then fold it into four times and make it the shape of a rectangle. And I have a piece of pen with me to demonstrate this. So I'm gonna fix it on the edge of the pen and I'm gonna rotate it with a force. This is my first example. The second one, I'll use the same thing, but I'll fold the paper 8 times instead of 4 times. This reduces the radius of the paper twice as much as the first example. Also, I'll use the same pen. Now, if I'm going to rotate this thing. Now, as you can see, after reducing the radius of the paper, this is rotating faster. For your better understanding, I'm going to do it one more time. So with shorter radius, and then with longer radius. Now, as you can see, the paper with the shorter radius was spinning faster than the paper with the longer radius. Now, if I'm going to describe this using my paper experiment, so this is an extended object. The law of conservation of angular momentum says that angular momentum is constant as long as there is no net torque applied to the system. So that means the initial momentum should be equal to the final momentum, that is Li equals to Lf. According to this, the angular speed increases when the radius the angular speed increases when the radius is short. So consider the example of ice skater. So when the ice skater taps in their legs, then he or she moves faster. Now, for the example that I have just showed, we know that L equals I omega. I is for inertia and omega is for angular velocity. So as per the description, as I've said, that angular momentum is going to be constant as long as no net torque applied to the system. That means the final angular momentum should be equal to the initial momentum. Now, since L is to be constant because there is no net torque applied to it, so when I decrease the radius, that means to keep L constant, my angular velocity should go higher. Now, I have told that I have used the same paper, I've just folded it twice as much. So since I have used the same paper, so mass was constant, but that when I have reduced the radius, so for the first time example, it was capital R, which is the longer one, but then I have reduced it to the shorter R. So since I have reduced the radius, now to keep L on the left side constant, because there's no net torque applied, my angular velocity needs to go higher. This is why in the second example, when I have used the paper with shorter radius, it was moving faster than the piece of paper with the longer radius. I hope this explains the conservation of angular momentum. Thank you.